So that's your choice. So if you are feeling very confident in your work, that it's correct, you understand the processes, like you feel like you've got this material down, then you can, there's another assignment that's due next Monday that is on Plimpton 322, which is this archaeological clay tablet that has the Sumerian triples on them. So this is more of sort of like a reading and exploring assignment. It doesn't involve doing any like mathematical operations. And if you want to listen to music while you're working on that, you know, so you've got headphones on, you're not listening to this, that's totally fine. Yes. Okay. So in problem number 11, we are asked to state the quadrant in which the angle lies. And so let's go ahead first and draw and label the quadrants. So Miles, which quadrant is quadrant 1?
Top right.
Top right. And then we go in order, but do we start out going to the left or do we start out going down?
It's like a C shape.
Yeah, exactly. So it's like a C, so it's 1, 2, 3, 4. Okay, so then one of the things that we worked on in class then is finding where sine, cosine, and tangent are positive and negative in the 4 quadrants. And we know that sine, cosine, and tangent are all positive in the first quadrant because all sides are positive. How about in the second quadrant? So we started working on this one. Is sine, Miles, positive or negative in the second quadrant?
I'm not sure.
You're not sure? Okay. So let's go ahead and go back to our triangle that we had. So this was our triangle that we were working with, and we found that this angle here at the center was 30 degrees, and we can label the coordinate plane with angle directions. And so we can think about the hypotenuse as being on a hinge here at the origin, and it's like now it's flexible and we can rotate it all the way around the circle. If we want to rotate it into the second quadrant to create a, you know, sort of like perfectly unwarped reflection of our original triangle. So we've got the hypotenuse, our first triangle, we've rotated the hypotenuse up to 30 degrees to create the triangle. Then we can keep going, and then we have to stop. You know, it's like the hypotenuse rotate, 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 and then we have to stop it, and then we've got the reflection. How many degrees have we rotated the hypotenuse in order to stop here to create like a perfect reflection?
It's 150.
That one's 150, that's right. So we can go 150 degrees, and now we've created the reflection. If it's a perfect reflection, has the length of the hypotenuse changed? No. Has the height of the triangle changed? No. Now the absolute value of the base hasn't changed. However, we are now on the XY coordinate plane.
Right.
So what is this, given that we're in a coordinate plane that has positive and negative based on the direction, what is the length of the base of this triangle?
Negative for square root.
That's right. Okay, so now, this this is slightly conceptual because this is 150 degrees, but now we're going to use this triangle that it's created in order to find sine, cosine, and tangent. So this is still going to be the opposite, and now this is the adjacent, even though it's not really technically adjacent to this angle because this is an exterior angle. So it's become slightly more conceptual. But if we're treating this as opposite and this as adjacent and this is still staying the hypotenuse, what is the sine of 150 degrees? So it's positive 1/2. So it's opposite over hypotenuse, it's 4/8, that's 1/2. So sine is still positive in the second quadrant because the height of the opposite side, the height of the triangle is positive.
Right. X is negative and Y is positive.
That's right, because here we're in positive vertical territory, but we're in negative horizontal territory. Okay, so now how about cosine of 150 degrees?
Cosine adjacent over the hypotenuse, so that's going to be negative.
Yes, so we're going to have -4 times the square root of 3/8, which is negative square root of 3/2. And so cosine now is negative.
Okay, I get it.
Yes. So let's go ahead then and complete the pattern. For tangent, we're going to have positive, opposite over adjacent, positive over negative.
Right.
Is tangent going to be positive or negative?
What's the rules if you divide by negative?
Yes, the weird thing is with multiplication and division, it's kind of like 2 wrongs make a right. So multiplying 2 negatives gives you positive, dividing 2 negatives gives you positive. But when you multiply or divide a positive or negative, you get a negative.
Okay. Yeah.
So in this case then, if you've got a positive divided by a negative, tangent is going to be,
That's
negative. Okay, so then we can continue down here, we can create a reflection of this triangle again.
Right.
Now it's not really the height of the triangle, what's the depth of the triangle? So now this is going to be -4 because we're going down.
Yeah, I get like the rule.
Yeah. So what we want to do then is we want to complete the pattern. For problem 11, we're asked in which quadrant are both sine and cosine negative. That's quadrant 3. Because both opposite and adjacent are negative here, so they're both going to be negative. So what I would suggest doing next, Miles, would be see if you can complete filling in these keys, which are positive, which are negative, and then you can double check your work against page 382. And that will help with other questions that are of this type. Before I erase what's up on the board, does anybody else have any follow-up questions about how we determine whether sine, cosine, tangent are positive or negative in each of the quadrants? Okay. Is it all right with you if I erase this now, Miles? Okay, good. Yeah, no, super important clarification. All right. So now we are moving on to problem number 25. So here we're asked to start by graphing the line y equals negative x. And this one was requested by you, right, Nate? Okay. Do you remember what y equals negative x looks like?
Yeah, it's a diagonal line from left to right, top to bottom, or from quadrant to quadrant 4.
That's right. So this is the line y equals negative x. And we're told that the terminal side, in other words, the hypotenuse of theta, it's on the given line in the specified quadrant, and we're told that we're looking here at this part in quadrant 2. In other words, then, this is our theta. Okay, so when working on problems of this type, and sometimes they're word problems, this one isn't really a word problem, it's kind of a word problem, because we're just given the words. But what's my first piece of advice when doing trigonometric problems? My first piece of advice is to draw the triangle. So right now, we've got this diagonal line, but we don't quite have the triangle. What do we need to do in order to go from what we have here to actually having a triangle in the second quadrant?
If you draw a line down to the x-axis.
That's right. So we draw up a line, and now we've got a right triangle. Does it matter what size the triangle is? Does that impact the ratios? It does not. So we can make this triangle any size that we want to help us visualize it. So what size would you like to make this triangle?
That's where I got stuck on the question. I was like, do the sides have to be specific? Or?
Well, they're going to have a specific ratio. If this is y equals negative x, what's the relationship between the length of this side and the length of this side? I haven't drawn it perfectly to scale. Let's say this is negative 3. What does this have to be? We're given a relationship between x and y.
Would it be 3?
It has to be 3, yeah. Because otherwise it's not fitting the equation.
So is y equals negative x the hypotenuse?
Yes. Yes. The terminal side of the angle is always the hypotenuse. And then the size of the triangle is irrelevant. We could make this negative 5 and then this would be 5. We're going to end up with the exact same answers to this question, but we can show why. So let's say that we're doing this version where the sides are 3. How long is the hypotenuse? How do we find the length of the hypotenuse? Yeah, so it's going to be 3 squared plus negative 3 squared. This is 9 plus 9. This is our hypotenuse squared. So we've got 18 equals the hypotenuse squared. What do we have to do to find the length of the hypotenuse then? What's our final step here?
You have to square root it.
That's right. We've got to take the square root of both sides. So we've got the square root of 18 equals the length of the hypotenuse. Are there any perfect squares that are factors of 18? 9. So we've got the square root of 9 times the square root of 2. And so we've got 3 times the square root of 2 equals h. So here's 3 square root of 2. Do you want to make an educated guess as to what the length of the hypotenuse will be on the 5 triangle?
5 squared.
It would. This makes it an isosceles right triangle because both legs are the same length, and that means that both angles have to be the same measure as well. Okay, so let's go ahead then and calculate what the sine of theta is going to be. And remember again, once we get out of the first quadrant, it becomes slightly conceptual. The vertical side is still the opposite side, even though now technically our theta is the angle outside the triangle that's forming the triangle. So,
Second quadrant is 180 degrees, and then minus 45 to the
yes, so our theta, yes, will be 180 minus 45, so we can say sine of 135 degrees. But then what is the length of our opposite side?
3
In this case, 3, and the length of our hypotenuse? 3 square root of 2. Okay, so these 3's cancel out, so we have 1 over the square root of 2. Now, is it proper math grammar to have a radical in the denominator? No. So how, and if you don't remember, it's okay, we can phone a friend. But how do we get a radical out of the denominator?
You multiply it by square root of 2 over square root of 2.
That's right, we multiply by a fancy version of 1. In this case, square root of 2 over square root of 2. Multiplying by 1 does not change the value, it just sort of reorganizes it, and so we end up with the square root of 2 over 2. Now I will say here, it's okay to flip this one for cosecant. You don't have to flip this for cosecant and then do this all over again. You can just flip this one. So cosecant of 135 degrees is going to be square root of 2 over 1, which is just the square root of 2. Let's keep going. How about cosine of 135 degrees?
Negative 3 over 3 square root of 2.
So it's negative 3 over 3 square root of 2, which is negative 1 over the square root of 2. But we can tell where this is going.
Yeah.
This is just going to be negative square root of 2 over 2. How about secant of 135 degrees?
Would it be square root of 2 over negative?
Well, I'm going to advocate for flipping this one again.
Because it's negative.
Yeah, so it is going to be negative, and it's going to be negative.
Square root of 2.
That's right, negative square root of 2. Very good. And then how about tangent of 135 degrees?
3 over negative.
That's right, it's going to be 3 over negative 3, which is
1.
close,
No. Negative.
negative 1. And the cotangent of 135 degrees is also going to be negative 1. The reciprocal of negative 1 is just negative 1. And again, the fact that the tangent of 135 degrees is equal to negative 1 is not dependent on the size of the triangle. We would have arrived at exactly the same answers if we'd used 5 and negative 5 and 5 times the square root of 2. We would have arrived at the same answers if we had used 5 million and negative 5 million, and 5 million times the square root of 2. So now we just know that the cosine of 135 degrees is negative square root of 2 over 2. So we have found a numerical relationship between those numbers. So is this sufficient, Nate? Does anybody have any follow-up questions on what is on the board right now? Okay. Is it okay if I erase this stuff, Nate? All right. All right. Now we have got number 47. And was this one yours, Quinn?
I did.
You did 47, Zena. Okay. So this is one of the cool things. You know, 750 degrees isn't even on a circle. We thought that we were pretty cool going from being limited to between 0 and 90 degrees in a right triangle and being able to do a whole circle. And that seemed like a pretty awesome trick that our triangle had figured out. But actually, if we go 360 degrees around the circle, do we have to stop there?
No.
We do not. We can keep going. If we complete another revolution, and I don't know if any of you guys like watching skateboarding or snowboarding or anything like that, you know, they'll often talk about like the aerial tricks that the athletes are doing in terms of the number of revolutions that they're doing. So they're like, oh, that was a 540, you know. But let's say that we just do 2 revolutions. How many degrees have we gone in total? 720. And then what are we asked for in this problem?
570. 750.
750. So how many degrees? So we go up here to 750, but how many degrees is that actually off of the horizon here? 30.
Oh, 30.
So sine of 750 degrees, for example, is going to equal sine of 30 degrees because our hypotenuse has landed in the same position.
Oh,
As 30
okay,
degrees.
because it's 750 minus 720, which is 360.
Yes.
Okay, I understand. Okay,
Yes.
I figured that.
So this is actually a pretty cool trick. And as a matter of fact, now that we've introduced directionality, let's talk about this for a minute. So we've looked at the example of 330 degrees, where we've started here and we've stopped 30 degrees shy of 360. But is there another way to get here from this horizon? We can go all the way around this way. But is there another path to getting from here to here? Yeah. Yeah, we can go negative 30 degrees. We can go the other direction. So it's not even that we have managed to sort of jailbreak our triangle out of 0 to 90 degrees to 0 to 360. We can actually go more than 360. And actually, if we just go the other direction, now we've introduced the idea of negative degrees. So our little triangle has like, this little triangle is like a butterfly. It has negative angles. It has negative sides. It has angles bigger than 90. It has angles less than 0. It has achieved, in a way, sort of limitless potential here. So, good job, little triangle. We're proud of you. Does anybody else have any follow-up questions on how, now that we've introduced this idea of rotating the hypotenuse around the origin, we can actually get degrees greater than 360 or less than 0? Yes, Sophia.
So then, how would you find the cosine and tangent of 750?
So the cosine and tangent of 750, so we've got, so sine 750 is going to be equal to sine of 30 degrees. Cosine of 750 is going to be equal to cosine of 30 degrees. And tangent of 750 is going to be equal to tangent of 30 degrees. And the 30, 60, 90 triangle is one that we know. So what are the proportions of the three sides of a 30, 60, 90 triangle?
The hypotenuse is twice the length.
That's right. So this could be like 1, 2, square root of 3. So what is the sine of 30 degrees?
1/2.
And the cosine of 30 degrees?
Square root of 3/2.
And the tangent of 30 degrees?
Square root of 3/2.
That's right. So it's 1 over the square root of 3, which equals the square root of 3. So one of the things that's interesting here is, although we can have bigger angles, greater than 360, they're not going to create any new triangle proportions. As the hypotenuse keeps going around, it's just going to be recreating and recreating the same proportions. Does that answer your question, Sophia? Yeah. Does anybody else have any follow-up questions on this additional flexibility where we can have our hypotenuse continuing to rotate around the circle, and in fact it can do so in either direction? All right. Is it okay if I erase this, Sina?
Yeah.
Okay. Okay, so Quinn, looking at problem 69. Oh, and we don't need to worry about the radians yet. So if the question was about radians, don't worry, we will get to that later.
Because I was confused on
Yes, we haven't learned the radians quite yet. We will get to those next, actually. So kind of like how we can measure distances, we can measure it in feet or miles, we can measure it in meters or kilometers, we can measure it in leagues or other random things. Furlongs. Anybody like horse racing? So there's lots of different ways we can measure distance. There's also multiple ways we can measure angles, and degrees and radians are the two main ways, and we will get to radians. But just answering these questions in degree mode.
So I have a question for 69. When it says that find two solutions of the equation, like, well, for this it would be find a solution of the equation. What does it mean? Because like a, like sine theta equals 1/2. That's not really like, it's not asking you for like a solution.
Well, so sine theta equals 1/2. If it's written like this, the variable is theta. So it's asking theta is equal to what?
Okay. I understand.
Yes. Yep. Good. Okay, so we're told And we've got quadrants 1, 2, 3, and 4. And we're told that we're looking, the information that we're given is sine. And we're told that sine is positive 1/2. So the first thing that we're going to do is identify which quadrant that we're in. So Quinn, in which quadrants is sine positive?
The first and second.
The first and second quadrant. And so we can ignore angles that are down here because they're not going to satisfy a positive value. And so then we're told that sine theta is 1/2. So we can go ahead, we can just go ahead and draw that triangle where opposite is 1 and hypotenuse is 2. And in this case, because we haven't learned yet additional tools for solving for more unfamiliar thetas, we can draw the inference that the textbook is asking us to find one of the usual suspects. In other words, there should be something about this that's starting to look familiar to us at this point.
Oh, it's a 30, 60, 90.
Yeah, so in a 30, 60, 90 triangle, the side opposite the 30 degrees is half the length of the hypotenuse. So we know that one of the thetas is 30. It's asked us to find 2. We know that sine is also positive in the second quadrant. So we create its reflection. Quinn, how many degrees do we have to go to create a 30, like to create this perfect reflection here where this is 30 degrees?
120. Wait.
Because we want a complete half circle is how many degrees?
90. Wait.
That's a quarter circle, yep. So here's 90, but what's this degree? How many degrees is this if we do a,
180.
this is a 180.
So.
So if we know,
50.
yes.
I'm really bad at like math.
That's okay, and you can always use your calculator, because we're not, this isn't, the pre-calculus is not meant to be sort of like a test of mental addition and subtraction. So you can, once you realize it's like, okay, it's gotta be 180 minus 30, you can always do that on the calculator. There's no problem with that. But yes, so this will be 150. And so our two answers then are sine of 30 equals 1/2 and sine of 150 equals 1/2. And these are our two solutions. Oh, well, and then we can see for part B, now sine of theta is negative 1/2. So we can undo this crossing this part out because in what quadrants is sine negative?
The bottoms.
Exactly, 3 and 4. And so we're gonna have to keep going to create this reflection and to create this reflection. So we know that we're gonna have to create this 30-degree angle again. If we're at 180 and now we need to do 30 degrees more, what is that angle measurement gonna be?
270.
Yeah. And likewise here, if we're gonna keep going and we're almost gonna do a complete 360-degree circle, but we're gonna stop 30 short, what is that angle going to be?
330.
330, that's right. So the answers to part B then are going to be 210 and 330 because those are the angles that are then creating those triangles of the same proportions in the third and fourth quadrant.
Oh, okay, that makes more sense.
Okay, good.
How did you get 210 again?
So we knew that
Oh,
to get the same proportion, we know this is going to have to be a 30-degree angle inside this triangle.
So it's 180 plus 30.
So it's 180 plus 30. That's right. And again, if we need to create this 30-degree angle here again, it's 360 stopping 30 short. So it's 360 minus 30. Good. Any other follow-up questions on this? How we're calculating, like at which angles we're stopping the hypotenuse to create the reflections? Where the ratios are, like which quadrant the ratios are positive and negative? All right. 93, we're actually going to return to after we have learned about radians. So if 93 was causing you frustrations, that serves as an illustration of why we need another way to measure angles, because this one doesn't work with degrees. So we can just put a little star next to that one, return to it. Yes, Sophia?
The challenge questions weren't required.
The challenge questions are not required. So that was just for people who wrapped the original assignment really quickly and wanted an extra challenge to work on. Then those were there as a choice, but yeah, no, they are not required. Yes, Nate?
What are the challenge questions?
The challenge questions are posted in the assignment on Google Classroom. So they deal with an application of some of this, which is with vectors, which is used in physics a lot. So those were just kind of a choose your own adventure kind of thing. Yes, Zena?
So if we like turned in an original picture with like the problems we didn't understand, like not fully finished, should we turn in a second picture with?
Absolutely. Yeah, absolutely. Yeah, you can totally, sort of like unsubmit and resubmit with more information. That's no problem. Yes, Francesca?
Could you do B and C from 96?
Yes. Absolutely.
Thank you.
Yeah. Okay, so first question in problem 96. Is this drawn to scale?
No.
Yeah, how tall would that guy be if this were drawn to scale?
Really tall.
Yeah, like 2 miles tall. So I'm hoping that that's not the case. That would be terrifying. So we can basically, on a scale of miles, we can just treat we can treat the person as a point. So one of the things that makes this figure a little bit confusing is it's kind of like, well, where's the triangle? Well, this person is not 2 miles tall. So we can treat this person as a point. And so here's our person. Here's the plane. And what is the altitude of the plane?
6 miles.
And then we're asked to find the distance. So this is sort of like, this is my first recommendation with any problem like this. Number one, draw the triangle. And number two is label the triangle. And this is going to include opposite, adjacent, hypotenuse. So if this is our angle here, and this is the window in which we're looking at this triangle, what is the 6 miles? What position is that to the angle? This is opposite. And how about the distance?
That's 12, right? Always double.
What's that mean?
Is the hypotenuse 12 because it's always double?
Well, on what kind of triangle is the hypotenuse double? They're only 30, 60, 90. So if this is 30, which it is in part A, so in A, theta equals 30 degrees, we know the proportions of a 30, 60, 90 triangle, ergo, the distance to the plane must be 12 miles. So this is one of the usual, our usual suspects, so to speak.
For the B, it's in 90 degrees.
Yes. So the other thing that we can do is to help us check our work is we can write this situation algebraically. So if we're going to write this information, let's say that we think that for 30 degrees the hypotenuse needs to be twice the height, but we want to double check. We're not sure that we've remembered correctly. It's really important that we also know how to write this information as an algebraic equation that we can solve. So the third part is to match the trig ratio to the situation. So which trigonometric ratio deals in opposite and hypotenuse?
Sine.
Sine. So we can say here that sine of theta is equal to is equal to opposite over hypotenuse. And here we're told sine of 30 degrees is equal to 6 miles over d. So we can rewrite this illustration as an equation, which then we can solve. So right now, we're trying to solve for d. What's the biggest problem that we have right now if we want to isolate d? Yeah, it's in the denominator. That is the absolute worst place for our variable to be. So right now, I'm just getting hives looking at this. So for problem number 1, we've got to get d out of there. So right now we've got 6 miles divided by d. What can we do to get that d out of the denominator?
Multiplied by.
Yes, so we can multiply by d, and we can multiply both sides by d. So whatever we do to one side of an equation, we have to do to the other. So now we've got d times sine of 30 degrees equals 6 miles. So okay, already my blood pressure is going down. Now we're very close to having d by itself on its own side of the equation. But what's the last thing that we need to do?
Divided by the sine.
That's right. So we divide both sides by sine of 30 degrees. And what is 6 divided by sine of 30 degrees? You can let your calculator do that.
12.
And 12 is what we're expecting because we know the proportions of a 30, 60, 90 triangle, but it's helpful to actually plug it into the calculator to see so that you can double check your work. So this is 12, okay. So let's go ahead then and let's look at B, where now theta equals 90 degrees. So the plane is continuing to fly. This is now 90 degrees.
Can't we just use the same problem?
We can use the same algebraic process to check our work, but I also want us to look at this picture and use logic to make an educated guess as to how far away the plane is when it's directly over the head of the person.
6 miles.
Yeah. So our guess is 6 miles, but now we can check it algebraically. We've got sine of 90 degrees equals 6 miles over d. We can use the same process to solve. So we're going to multiply everything times d. So I've got d sine 90 equals 6 miles. Divide both sides by sine of 90 degrees. So d is equal to 6 miles over sine of 90 degrees. And that you can plug into your calculator, and what do you get?
6.
Yeah. So our educated guess based on the illustration has now turned out to be algebraically correct. And the sine of 90 degrees ends up being 1 because now the opposite side is perfectly lined up with the hypotenuse. And so the opposite and the hypotenuse have become 1. All right, so now we're going to go to C, which is 120 degrees. And so now the plane is now like behind the person. So we've gone 120 degrees. But the altitude has remained the same. So this is still 6 miles. This is still the D that we are seeking.
Not even a triangle anymore.
It's not even well, this is true, but we can always complete the triangle by dropping a vertical line. Now we have this right triangle. So it's like we can think about where the person is as the origin. So this is 0 degrees, 90 degrees, and a complete half circle is how many degrees?
180.
This is 180. So we can think about it now by putting the person at the origin. We can just think about, okay, this triangle is now in the second quadrant. So we can solve it using the same algebraic process, but if we stop at 120 degrees, how far is left to get to the full 180?
60.
So this is a 30, 60, 90 triangle. The only thing that I will say is this 6 miles is across from the 60. Which means that this 6 is actually something annoying times the square root of 3. Because remember, on a 30, 60, 90 triangle, this is, the one across from the 30 is nice and the hypotenuse is nice, but this is the square root of 3, 1. So that is not, this, we can see we're on a 30, 60, 90, but given the information that we have, it's not going to make it super easy for us to solve it just using logic. because of where the whole number is. Oh, shoot.
Yeah, it's 10:25.
But we can, it's 10:45?
It's 10:25.
10:12, I was like, oh my gosh, is that clock slow? But we can solve this, Francesca, using the exact same sine 120 is going to be equal to 6 miles over d, and we can solve it in the same way using the calculator.
Even if it turns out a decimal, it's fine.
Even if it turns out a decimal, which it's going to do in this case because we're on the square root of 3 side, but we don't see the square root
Can we let it go?
of 3. Yes.
Thank you.
Au revoir. See you in assembly.
The
Scenario
Yes.
reading is really interesting.
Super, I know. It's very exciting. I love it. It's like Indiana Jones.
Really?